So far we have seen control hazards and we implemented pipeline related to that, correct? Now please recall that model. So example, let's say this is your pipeline and currently let's say this is a branch instruction. If you fetch branch instruction, then in our model in the next clock cycle we fetch the next instruction, correct? But we know that this next instruction might not be the right instruction. And let me ask you a question. Why did you fetch the next instruction? Because you are predicting. You know that only sometimes this is going to be correct. Sometimes it is going to be wrong. Now let me ask one question. Why don't you really fetch the right instruction rather than wrong instruction? Because we don't know where is the right instruction, correct? Because we don't have that information. So here what I want to say is whatever you implemented, here you are predicting that next instruction is the right instruction, correct? Of course. So that prediction may be correct, may not be correct. That's why it is called prediction. Finally, the implementation whatever you have followed for implementing control hazards or implementing pipeline for control instructions, the way you predicted that the next instruction will be executed. But always you are fetching the next instruction. That means your prediction is called static. So finally, the previous model, whatever the model so far you discussed is called static prediction scheme. Now we can have an alternative, that is dynamic prediction. What is the problem with static prediction? You are not really understanding the nature of the program. Always you are assuming that branch will not be taken, right? Initially you are fetching the next instruction because that is easy to implement, right? Now, but unfortunately what happens is, so most of the times branch might be taken, right? And example, let's say you are executing a program where on that program every time, most of the times, let's say branch is getting successful. That means branch is taking. Then your prediction always will go wrong, right? So that's why what I want to say is don't predict statically. Rather than that, predict dynamically. What you do is, so somehow I am just giving the idea, somehow you have to predict the right thing and you have to update yourself. Then we say that that prediction is dynamic. Example, let's say you are watching something, let's say then two people are fighting, that means wrestling, okay? Let's say two people are fighting, maybe wrestling, whatever it is. Then you are just predicting the result. Let's say he is X, he is Y. First match you observed, then you got the result is x won. Then second time you are predicting, you generally the tendency is we predict that x will win, then again x won. Then the third time you predict that definitely x wins. In that way, so you will fix this prediction, right? That means always you vote for him. Then suddenly what happened? After some time y started winning. Then let me ask one question. After 100 iterations, let's say 5 times, let's say x won, 95 times y won. After that you have to now take the next decision. Now you have to tell whether x wins or y wins. Then whom you predict? Y, right? Then why you changed your prediction? Because of the observations, right? So using the history, if you change your prediction, then we say that that is dynamic prediction. Here also we are going to use that model because that is really nice thing than static prediction. Let us do dynamic prediction. So in the dynamic prediction, we are going to discuss two models. One is single bit prediction. Second one is 2-bit prediction. Okay. We will see two models. One is single bit model, second one 2-bit model. So single bit model is nothing but 2-state model and 2-bit model is nothing but 4-state model. We will see both of them. First of all, let us begin with single bit model where you will have 2 states. So here pipeline is going to have two behaviors. One is sometimes pipeline says that pipeline guesses that the branch is likely to be taken. Sometimes pipeline guesses that branch is not likely to be taken. Initially, let's say pipeline will be in this state. That means pipeline is thinking that this time if branch is executed, the target address will be taken, likely to be taken. Okay. Then at that time really the outcome is taken, that means really the branch is taken, then again that will be in the same state. If when pipeline is thinking that branch is likely to be taken but really in the outcome it is not taken, then it will change its mindset to not likely to be taken. When your pipeline is assuming that branch is not likely to be taken, but really branch is not likely to be taken, I mean branch is not taken, see, not taken, then again we will be in not likely to be taken state. It's easy to understand, correct? So whenever you get opposite outcome, that means you are predicting that branch is not likely to be taken, but really the outcome is taken, that is the action, then we will be changing our mindset to again likely to be taken. In that way we will be oscillating between likely to be taken and not likely to be taken. Understand? So here this is what dynamism. Now we'll see with one example. Example, let's say currently you are executing branch instruction, but you don't know that, right? So you are fetching one instruction at first clock cycle. Now in the second clock cycle, you are decoding that instruction, correct? Now, so far after end of the decode cycle only, you might be knowing that that is branch instruction, correct? After complete decoding. But before itself, here we have to fetch the instruction. Now can I say one thing? In the second clock cycle, if assume that, let's say, of course we don't know, but let us say this is branch instruction, okay? Then here we have to fetch the instruction depends on the mode of the pipeline. If pipeline is in this mode, then it is guessing that it is going to be a branch is going to be taken, then it will fetch the target instruction, correct? Now if this branch pipeline is in this mode, that means which mode? Not likely to be taken. Pipeline is predicting that branch is not likely to be taken, that means branch condition is false. Then we will be going to the next line, right? So what we will be doing? We will be fetching the next address. Finally here this fetch depends on this branch instruction, but we don't know that it is branch instruction or not, first of all, correct? One thing which we don't know before decoding or before second clock cycle is whether it is a branch instruction or not. Second one, assume that let's say somehow God explained us, otherwise God helped us such a way that we understood that this is branch instruction. I will tell you how to do that. Then still you can't fetch the right instruction here. Why? What's the problem? One more problem. Where is next address? That means really branch is taken, then it should go to the target address, right? Where is the target address? That is written in the instruction. But before decoding it, otherwise in the decode stage generally we are taking that, correct? So before decoding stage itself, that means here. After fetch stage itself, we should know that that instruction is branch instruction and we should know where is the target address. We will see that implementation. We will be maintaining a table called branch history table. So that table is going to have all these details. So I will explain that. At that time you will be convinced that here we will be automatically getting the details without decoding the current instruction. Okay, so don't worry about that. I will teach that. At this moment, let's say somehow you have that information. Now let me ask direct one question. Let's say pipeline is in this state. Now which instruction will be fetched? Definitely, because pipeline is assuming that not likely to be taken, then here we will be fetching the next address, correct? That means this first instruction is at 100, then next instruction is 104. In that way we will be fetching, because we are assuming that it is not likely to be taken. So this is a model. Now first we'll see the problem with this one. What's the problem with this one is, that means why it is not highly accurate, I will tell you. So for that, take this example. So there are two loops, okay? This is second loop and this is the first loop. So you see this loop, this entire thing is the first loop. Let us understand what this loop is doing. So in the loop you have branch and equal condition. If this R1 and R2 are equal, then we will be taking the second loop. That means again we are going to the loop. Understand? It is like writing two for loops. Okay? For. First for is 100 times, second for is 100 times. You know the concept of writing two for loops 100 times, right? So forget about the second loop, just focus on this loop. Okay, R1 is initially 0, R2 is 99. Okay, so branch and equal. Sir, what is second loop? It is, let's say, some target address. We are jumping to somewhere. But in the first iteration, R1 is 0, R2 is 99. They are not equal. Then condition will become false. Then branch is not taken. Correct? I am just talking about the reality, right? So, forget about the predictions first. We know that if really this program is executed, then first time branch is not taken, right? Okay, let's write the result. In the first pass, I am talking about inner loop. Okay, in the first pass, what is the reality? Reality is branch is taken or not taken. Taken or not taken, we write here. In the first pass, branch is not taken, right? Yes. Next. Otherwise, we need one column, enough. Second one. So what we do, we come inside and add R1, R1, 1. That means R1 is incremented. Then R1 will become 1. Then after that jump to loop, right? We'll go to the loop again. Again branch and equal. This time 1 equal to 99. No, condition will become false, right? So in the second pass, branch is taken. No. In the third pass, R1 will become 2. You can understand by this time, right? Third pass also branch will not be taken. Fourth pass, no. Fifth pass, no. How many times we have to wait? We'll see. Eventually, R1 will become, because every time you are incrementing, right? R1 will become suddenly 99. Initially, R1 is 0. In the first pass, R1 is 0. Second pass, R1 equal to 1. Third pass, R1 equal to 2. R1 equal to 2. In dash pass, R1 is 99. See, first pass R1 is 0. Then when R1 is 99, this is 100th pass, right? That means, so this loop is iterated over 100 times, right? In out of 100 times, 99 times condition is becoming false. One time condition is becoming true. So that's why I can say that the total summary is, so branch is taken one time, not taken 99 times. Not taken 99 times. So here branch target is second loop. Now this loop actually inscribed in second loop. There is another loop, okay, but I did not clearly write that second loop, okay. So because I don't want to focus on writing the assembly instructions clearly. What is our target is understanding how this kind of program is executed by pipeline. How many times that pipeline is going to tell the right answer, okay. How many times it is going to predict correctly. So here you should understand one thing. This is a loop. When first time it is executed, this is the result. But after that we will come back to loop again, because assume that, let's say, after this target, I mean whenever condition is true, that means R1 and R2 are equal, then we will go to second loop. In the second loop, which we run 100 times, that means again this second loop is going to be executed 100 times. Otherwise, you try to understand. I don't show second loop, but this is the second loop. Second loop is nothing but a place where, because of that, this is second loop. In the second loop, what is happening is, again R1 will become 0, R2 will become 99, and we will begin it again. Try to understand. So how many times this second loop will be executed? Assume that somehow you plan this second loop so that it is executed exactly 100 times. So how to do that? That's a separate story. How did you create a loop here such a way that it is executed 100 times? In the same way, we can write extra code so that this second loop also is executed exactly 100 times. So finally, this problem you see, I just show the flow. We come like this. First we start at here R10, R2 99. That is first iteration of second loop. Then we come here and we run 100 times. 99 condition is true. One time condition is false. We will go to second loop again. Then again we will make R1 equal to 0, R2 equal to 99. We repeat it. That is what the looping here. So in this looping, how this your pipelining works, we'll see. Assume that, let's say, you are using 1-bit prediction scheme. In the 1-bit prediction scheme, let's say you are initially assuming that branch is likely to be taken. You have other option, but what is it? Not likely to be taken. Let's say first time, let's say your pipeline is here, okay. Then tell me, this branch is true or what? I mean, this branch is satisfied or not? Not satisfied. That means branch is not taken. but what is your prediction likely to be taken? Then your prediction, first time your prediction is wrong, right? Then what you do, you will come to your pipeline will come to this mode, right? This mode, then it will learn that, oh, branch is not likely to be taken. Now second time what happens when R1 is 1, then really branch is not likely to be taken. We know that branch is not taken, and you also saying not likely to be taken. Then your prediction will become wrong, correct. Then again your prediction will become correct every time, because from now onwards you are saying that branch is not likely to be taken, but same thing is happening in that way. So this loop, inner loop will be executed 100 times. First time your prediction become wrong, but remaining 99 times your prediction become right, correct. Now sorry, not 99 times, in the last time what happens, you see 100th time, when it is 100th time R1 is 99, okay. When R1 is 99, both are equal, but you are saying that branch is not likely to be taken, but this time branch is taken, then your prediction will become wrong. Now let me summarize. When this loop is executed one time, on that first time you said branch is likely to be taken, but actually at that time branch was not taken, so your prediction become wrong. Now after that what happened, you changed your mood to not likely to be taken, but the result also same, I mean the reality also same, that's why your prediction become correct. But in the last iteration, really branch is taken, but you are in same not likely to be taken mood, then you said wrong, you gave wrong answer, then your prediction become wrong. Finally what I want to say is, if this loop is executed, inner loop, if this inner loop is executed one time, okay, then out of that, that means inner loop executed one time means inner loop is executed 100 times, out of them your two predictions gone wrong. What if I repeat this inner loop for outer loop? That means when you have two for loops, then what we will be doing, we will be starting again. That means, because of this second loop, we will be coming to again same thing. R1 is 0, R2 99. Again we come here and we begin it. In that way, if this entire I can say module, if this module is executed, let's say 100 times, every time same thing will happen. In each time you do two mistakes. Then out of 100 times, so how many mistakes you will do? 2 into each time 100 times. 2 into 100, 200 mistakes you do. And how many corrects you do out of 100 into 100? Out of 100 into 100, for every pass 98 times you will be correct, right? 98 into 100, that means 9800. I can say that 200 wrongs, 9800 correct. Now what is the accuracy? What is the formula for accuracy? Think. If every time you are, every time you are right, sorry, how many correct things you told? 9800, correct? Out of 10,000. So this is your accuracy. 0, 0 gets cancelled, 0, 0 gets cancelled, it will be 98%. Understand? But actually we can predict more accurate than this one. Try to understand why we can predict more accurate than this one. I will tell you. If you use 2-bit information rather than 1 bit, because simple for loop, it is almost every time is correct, only one time it is taking the jump, right? That means one time only it is taking the jump, but you predicted 2 times as wrong, right? Then what we do is, by introducing more information, that means 2-bit prediction. In the 2-bit prediction model, we will be having more information, and we are not quickly changing our mindset, so that for same problem we can have better accuracy. Understand? Now let me ask one numerical question before going to that. Rather than 100 times, if I change this program to 0 to 9 loop, and this is also 10 times, okay, whatever, otherwise the first loop is 100 times. Try to understand. The outer loop is 100 times iterated, but this inner loop is iterated only 10 times. Then same story. Then my question is, how many wrong predictions you do? So it's not a big deal. For one time you tell me, for one time there will be, first time you do wrong, then remaining all the times except the last time you do wrong, you do correct. So finally how many wrongs? 2 wrongs. Out of how many iterations? 10 iterations, correct? I can say that. So finally 2 out of 10, that means I can say that 8 out of 10 are correct. Your scorecard is 8 of 10. Mr. Prediction Scheme, this is your performance. You were correct 8 times out of 10. Then out of 100 you will be correct 80 times. So the accuracy is 80%, right? If your loop is not very big, if your loop is very small, then your accuracy will be reduced, correct? Now what I want to say is, sir, how can you say it is 80%? Because you did not calculate for 100 times, no? That's easy. For every loop, so 100 times you did the same thing, right? Then your accuracy will not be changed. See, 8 out of first loop, second again 8, third 8, that way. I can say that how many iterations finally, how many branch decisions we had, how many times this branch is executed? 10 into 100. Out of them, how many are correct? For every 10, 8. Correct? 8 into 100. Same story, 100 will be get cancelled. You get again 8 by 10 scorecard. That means 80 by 100. So what I want to say is, so this problem is having accuracy of 80%. Understand? Now, the question is, can we do better than this? Yes, if you have more information. That's why we are going to have 2-bit prediction model. Let us see that. So in the 2-bit prediction model, we will be having 4 states. Let me introduce them. The first one state of mind is branch is strongly likely to be taken. When you are in this mode, you are 100% confident. Of course, it's a prediction. So you are 100% confident that branch is strongly likely to be taken. Now after that, there is another state called likely to be taken. That means you have small confusion. You are not 100% sure. You are maybe 80% sure. That's why. So this state says that whenever the pipeline is in this state, that means pipeline is thinking that branch is likely to be taken, not very strong. Okay. Now that means your pipeline's opinion is not very strong. Again, you have two opinions about not likely to be taken. One is simple not likely to be taken. Second one, strongly not likely to be taken. Then your pipeline sometimes assumes that branch is not strongly not likely to be taken. Sometimes it assumes that branch is not likely to be taken. Okay, here it is very serious. It's very sure. Here also it's very sure about taking. Here your pipeline is not, definitely very sure that it is not likely to be taken. So in that way, 4 states. Let me repeat: strongly likely to be taken, likely to be taken, not likely to be taken, strongly not likely to be taken. Now, initially, let's say you are in strongly likely to be taken. Anywhere you can start. Okay, not a problem. So when you are in this mood, really, if the decision, otherwise outcome is taken, you thought it is branch is likely to be taken, right? Strongly likely to be taken, but outcome also taken, then you will be in same mood, right? That means you don't change your mindset. When you will change your mindset, when the outcome is not taken, when branch is not taken, go to likely or likely to be taken. When you are in likely to be taken, then you are going to change your mood if the decision is not taken. Again, second time also, if you predict wrong, then you will come to not likely to be taken state. When you are not likely to be taken state and really branch is not taken, see, try to understand, then your opinion will become strong and you say that strongly not likely to be taken. From now onwards, you say that yes, branch is not really getting taken. Now when you are in this mode, then you will come to this state if opposite result comes. That means you are saying that not likely to be taken, but branch is taken, you will come here. When you are in this state, not likely to be taken, but what happened, outcome is taken, then you will come to likely to be taken state. When you are in likely to be taken state, again one more outcome comes with taken, then you will strong your opinion. That means you will come to strongly likely to be taken. Now see, so I have to show some more. What when you are in strongly not likely to be taken opinion, then really the favorable opinion comes. What is that? Not taken branch. If branch is not taken, you will be in same state, right? Now this is about, I think, all possibilities. For this state there are two opinions. One, 2. When you are here, two opinions or two state of minds. One is for taken one thing, one is not taken one thing. Here also one to here, one to here. When you are here, one to here, one to here. I hope you understand this idea, right? So now in this model, what is going to happen, we'll see. Let us take same loop. In this loop, first we focus on first iteration, because second loop is going to be executed 100 times. Let us focus on out of that 100 first time, in the first time, and assume that, let's say, you started with an opinion called strongly likely to be taken. You are assuming that, let's say, that loop is going to be strongly likely to be taken. If that is the opinion, then is it right? You're wrong. Try to understand. In the first time, your prediction become wrong, because your prediction is what? Strongly likely to be taken, but branch is not taken. Then your prediction is wrong. Now you will come to this point. Now when you are in this point, second time also what happened? Now you are again saying that branch is not likely to be taken, but this time you are not so strong. But what is your prediction here? Likely to be taken. But what is reality? Branch is not taken. Then your second prediction also wrong. Sir, you said it's better than the single one, that single bit one, but it's not performing well. Wait, in the long run definitely it will succeed, because it's all just one or two iterations, right? So we can't decide it. Now in the third iteration, now come, we are here from likely to be taken, but outcome is what? Branch is not taken. Then we'll now change our opinion, we'll come to not likely to be taken state. Now what is reality? Branch is not taken. Then your prediction will become right, because you also said same thing, not likely to be taken, and your prediction is correct. Then we will change our opinion to strongly not likely to be taken. Now see, we are in this state now finally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times, right? In the 10 times, first time you predicted wrong, second time you predicted wrong, third time you are saying that branch is not likely to be taken, but it is correct. So your prediction is correct. So in that way, every time it is correct. Last time branch is actually taken, but you are still saying that it is not likely to be taken. Then you will come to this mode. That means you change your mind, but of course your opinion is wrong, right? Or your prediction is wrong. Then finally, so 3 times you did wrong, but don't worry. So we are executing that 100 times, right? When you execute in the, so many number of times, slowly it will be stabilized. Second time what happens? Again we will start with R10, R29 and we will come to branch. Now what is the state you are in? Not likely to be taken, but branch is also not taken. Then your prediction is perfect. Second time also branch is not taken. Now you are here, actually not likely to be taken in that mode, but your prediction become wrong, correct? Branch is not taken, then we will settle here. Now second time branch is not taken, then you will be in that mode. In that way every time you will become correct. See, the last time branch is taken, but you said branch is not taken. You are wrong, only one time. But since you are wrong, then that means what? You are saying that you are in strongly not likely to be taken state, but branch is taken. Then we'll come to not likely to be taken state. Now again in the third time, same story. See, when we started second time, we were in not likely to be taken state, and whatever you did, same thing you do here also, correct? First time, branch is not taken, but you are also saying the same thing. Your prediction is correct. Since branch is not taken, we'll come to this point and we'll settle here for remaining iterations. Then every time you will become correct except last time. So in that way, we are not quickly changing our mind. There are two things, right? After 2 wrong predictions, we are changing our mind here. But in the previous one, very quickly you are changing the mind. That's why you get little bit more wrong predictions. That's why finally I want to say that ignore this point. Okay. But second time, third time, for all that 900 times, out of 100 times, other than first time, so remaining 99 times, you predicted 9 out of 10, you see. 9 out of 10, 9 out of 10. Let us really calculate for this problem. In the GATE exam sometimes they can ask numerical questions. Let's say this is your problem. There is a outer loop for 100 times, inner loop for 10 times, then you are using this 2-bit prediction, then what is the accuracy? Let us list out all the cases. First time 1, 2, 3. In first time 3 out of 10, correct? Second time, so I am sorry, we have to find out the right predictions, right? Accuracy is nothing but how many correct predictions? 7 out of 10 is your scorecard first time. Second time, remember it, okay? 7 out of 10. Let us write like a data, 7 out of 10. Now, second time. In the second time onwards, 9 out of 10, 9 out of 10. How many times you did that total? So total 99 times. So number of right predictions are 9 into 99, and the number of predictions are, how many predictions? 10 into how many times? 99 times. Try to understand. So finally, let us list out all the right predictions. The total number of right predictions are 7 here plus 9 into 99. This is your story, correct? These are the right predictions. Out of how many? 10 here plus 10 into 99. Otherwise, in total predictions we know that 10 into 100. If you simplify it, you get 7 plus 9 into 99, right? So you have to simplify it. Let us say, you simplify it. It's homework for you, okay? So in this way, so definitely this will be better than the previous single bit prediction. Understand? So finally you learn 2 dynamic branch prediction models. Now the only thing we should know, so how we implement it. Just this finite automata is our imagination, right? But how your pipeline uses this finite automata further. So your pipeline is going to maintain a table called branch history table. Sometimes this will be said as branch history table. Otherwise we say branch prediction table, BPT, branch prediction table. Otherwise we say branch history table, BHT. All are same. We will see how that branch history table is going to help us to quickly find out that the right prediction. Okay. Otherwise, whatever the prediction these states are giving. Okay. We will see that table. Now we will see how this branch history table is implemented. Okay. So branch history table will contain 3 entries. One is a branch address, second one target address, and prediction. Okay. So branch address is nothing but the branch instructions address. Now target address is nothing but if branch is taken, then what is the target? Understand? Now, sir, what is this 000001010 up to this 111? Addresses of these memory locations. Assume that each one is one memory location. So using some faster circuits, we can implement this kind of memories. Okay. Don't assume that this is main memory, because if you keep this entire data in main memory, it takes lot of time that you will be studying in your main memory, that memory management, otherwise memory organization. At this moment, assume that it's a circuit. That means it is some hardware circuit which is very close to CPU, like cache. Okay. So we implement using very fast hardware circuits this table. So that's why only 8 locations I am taking. In general, in the reality, in real implementations, the number of memory locations to maintain this information will be typically maybe 256, otherwise 1024. It varies. It depends on the architectures and the vendors who are designing the systems. Now assume that for simplicity, let's say we have only 8 locations. But sir, what if we have lot of branch instructions in my program? Then only favorite, otherwise few of them we are maintaining, and that's it. Okay, because every branch we cannot, sometimes because speed is important. Remember one thing, when less number of memory locations you use, then hardware cost will be less, and one more thing, that will give you faster access, because faster access is important, correct? So if you have lot of memory locations, then it will take lot of time, then within one clock cycle you may not fetch the data, then that's useless. Again, you are what is the purpose of doing all these things? To reduce the stall cycles. That means you don't want to stop your pipeline. Then when you maintain a very big memory, then to access this memory it will take a lot of time, then again you will be wasting the time. That's why it's a contradiction. To not to waste the time, we have to quickly access this memory, then the number of memory locations should be less. That's why we are using only this many. Now we will see how this table can be used with one example. Example, currently program counter value is 100. Okay, now we are at first clock cycle. At this moment still no one knows, your pipeline doesn't know whether it is a branch instruction or not, because even it is, that instruction is not fetched. So what is the instruction you are fetching? The only thing which we know at this moment, our pipeline knows, is the that instruction address, which is 100. That may be branch instruction, may not be. Now in the second clock cycle we should properly fetch the instruction. We should guess something and we should go there. Before that itself we should do everything. So how we will be doing, we'll see. In the first clock cycle we will be fetching that instruction which is at 100. Okay, at the same time we will have additional circuit. That circuit will look, because of that circuit we will be accessing this memory. That means take the program counter. We are in first clock cycle, remember that point. Generally in the first clock cycle what you do, forget about this table. Generally what you do, we will go take the program counter and we will access the memory, instruction memory, and we fetch data, right? That means instruction. Parallelly what you do is you access this memory. Take this program counter 100, but sir, are you going to search like this 80, 129, 34? No, we will be indexing. So for that what I do is, this program counter, if you see in a 32-bit, you see binary pattern. Let me convert 100 to binary pattern, because this is for our convenience. In the reality they will be 32 bits, correct? If I write binary, that will be, I know the value of 100 in binary, it will be like this. So first 8 bits are important. 1 2 3 4 5 6 7 8. 240 1 2 4 8 16 32 64 128. 100 is nothing but 64 plus 32 96 plus 400. This is the binary pattern of 100. So what about the remaining bits? Zeros. Okay. So what I will be doing is, apart from fetching the instruction, we will just at the same time simultaneously we will see these 3 bits. Okay, extra circuit 100. Then go to 100 directly. We quickly index into this table 100. Now let me ask one question. Whoever is watching my lecture, we are in currently we are in which cycle? First clock cycle. Simultaneously we are fetching the instruction. At the same time we are accessing this memory. Okay, so directly index to that 100. Yes, 100, and compare this 100 with your program counter. Did they match? Yes. That means what? Now being in your first clock cycle, though you did not fetch your instruction, because of this table you realize that that instruction is branch instruction. I already asked you one question. Sir, without fetching the instruction, how can you say whether it is branch or not? Generally, if you don't have this table, example, if you want to know whether one instruction is branch or not, what we have to do? We have to fetch it. It takes one cycle. In the decode stage, we have a mechanism to check whether that instruction is a branch or not. But I don't want to wait up to that point, because before that itself, I want to fetch the next instruction correctly here. To do that, this table is required. Then in the first clock cycle itself, I will fetch here and I will see 100. This mapping, that means this 100 says that yes, current instruction which you are talking about is branch. Now I will go to prediction bit. So what this prediction bit says? The mood of the pipeline. Already we have seen the states, right? So this is 1-bit prediction model. In the 1-bit prediction model, currently this 1 says that the pipeline is assuming that branch is taken. Maybe history says that in the previous time branch is taken. If this bit is 1, then go to target address 700. Then immediately what you do is, now first clock cycle is done. In the second clock cycle, here according to your knowledge, you realize that 700 is the target. Immediately modify this program counter to 700. Then second time when you fetch, the instruction will be at 700. In that way, without wasting even single clock cycle, we properly fetch the right instruction. Sir, what if really your guess is wrong? Yeah, if my guess is wrong or my prediction is wrong, everything goes wrong. It's all about prediction. No one knows the reality. In the reality, anything can happen. Even you are preparing for GATE exam by predicting some things. You are assuming that questions comes from this topic, question comes from this topic, and in that way you are predicting something and you are understanding the things, right? Suddenly they can ask very difficult questions which you don't predict. What happens if that kind of things happens? Then we should not attempt that. I mean, we don't attempt that question, right? That is the real. Sometimes it happens, but it doesn't mean that it always happens, right? So that's why prediction is prediction. But we have a educated prediction. That means we are learning. That is dynamic prediction. So the statistic says that 30% of the time you are going to rightly predict. It depends on your implementation. If you use 2-bit prediction model, then up to 60 to 70% of the time the real world implementations are going to get the right predictions. That's why we use this kind of prediction tables. Okay, they are not blind predictions, correct? So most of the times you are going to get the success. Finally, this is about implementation. Understand? Now, sir, what really this prediction is not taken? Let's say this prediction is wrong. Then we flush it as usual, right? Now we will come here and we change this bit. Mr. Instruction 100. Previous time I thought you will take the branch, but you did not take. That's why I update this value. In that way we do it. Understand? So we dynamically update these values based on the current information. Understand? So this is about all that dynamic branching techniques and everything. Sorry, dynamic prediction techniques, everything. Okay. Now you can answer any gate question from this branch predictions and everything.